As you know, the next class is an exam, so or quiz. So today we're going to dedicate the whole class just to doing problems and answering your questions. Are there any questions before I start working on it?
Is the mechanical stuff that you were introduced going to be on an exam, or just going to be?
No, one thing about quiz. Quiz is only on the material covered in between the two quizzes. So this is going to be the chapter, what is it, chapter 4. Just the chapter 4.
So it's on the solar cell kind of problems.
Was that, no. That was just chapter 4, just the link budgets and noise temperature and all these things like that. In chapter 4. All right, so let's do as many problems as we can. I'll try to post these problems as well on the website so that check them out either later tonight. It says a C-band Earth station has an antenna gain equal to 54 dB. So Earth station. The output power is set to 100 watts, and the frequency of operation is 6.1 gigahertz. The signal is received at the satellite at a distance 37,500 kilometers from the surface. The satellite, so this is Earth station, the satellite has an antenna that has a gain 26 dB, and the signal is routed then to transponder that has a system temperature of 500 kelvins and a noise bandwidth of 36 megahertz. The gain of the transponder is 110 dB. So these are all input data. The part A, it says calculate path loss at 6.1 gigahertz. That's how much loss will be suffered on a link from the ground station to the satellite. Of course, it's always, even if it's trivial, I always suggest drawing the picture so that you understand what you are working with, right? So this is your Earth station, and we're looking at this particular link, which is at 6.1 gigahertz, right? Uplink for the C-band. What's the downlink for C-band? 4 gigahertz. Around 4 gigahertz. Okay. So free space path loss equation is 9244 plus 20 log of frequency given in gigahertz, and then plus 20 log of distance given in kilometers. In this case, this ends up being 9244 plus 20 log of 6.1 and plus 20 log of 37,500. When I did the calculations, this ended up being 199.62 dB. Okay. Part B. It says calculate power at the output of the satellite antenna. Calculate the power at the output of satellite antenna. Now, that's why these figures are always, helpful, right? Because you can kind of, what is it that we calculated? We calculated this free space path loss from this point to this point, right? So now, we do it, you can do that many different ways, but I always, this is my training. I always calculate the ERP then calculate the free space path loss, then look at what the sensitivity is and where is the reference point at the receiver. So always calculate the ERP first. In our case, this becomes the transmit power, which is 100 watts. How many dB watts is that? 20 dB watt. And then plus the antenna gain of 54 dB. So it's 74 dB watt. And then your received power in dB watt becomes your EIRP minus your free space path loss and plus the gain of the satellite antenna in dB. So in our particular case, this becomes 74 dB watt minus this 199.62 dB and then plus 26 dB of the antenna gain on the cell. So when you calculate this, this is minus 99.62 dB. And then part C. Part C says calculate the noise power at the transponder. Calculate the noise power at the transponder. So the noise power at the transponder is going to be 10 log KT system times the noise bandwidth of the transponder. So in our case here, this becomes 10 log Boltzmann's constant, 1.38, right? 38 times 10 to the minus 23 joules per Kelvin times the system noise temperature of 500 Kelvin and times the noise bandwidth of 36 times 10 to the 6th hertz. Now, as we're doing these problems, make sure you don't forget that you have to express the bandwidth in hertz. Right? That's the one of the, I say it every time, and it's always that somebody forgets it. Right? So make sure that the bandwidth is in hertz. Right? So when I did these calculations, this ends up being minus 126.04 dB watt. So that's the noise power. And then it says calculate the signal power or calculate the signal power at the output of the transponder. Somewhere in here, we were required to calculate C to N. Yeah. So I guess if you know this, what's C to N in this case?
C minus N.
C minus N in dB, so it becomes minus 99.62 minus 126.04. So it gives you 26.42 dB. Now, that's the C to N at the input to transponder. What's the C to N at the output of the transponder?
At the gain of the transponder.
To what? So gain of the transponder is 110. So the C to N at the output of the transponder is 136 dB.
No.
Why not?
Noise.
Because the transponder amplifies both signal and noise. Transponder itself, this is the best you can do, right? Transponder itself does not improve the C to N. As a matter of fact, this is the best you can do, and it occurs only if you don't drive the transponder closer to saturation, and the only impairments that you have is the noise. If you try to amplify and drive the amplifier into saturation, in addition to the noise, which is coming from the system noise temperature, you're going to have intermodulation products that will fall within the same band with the transponder. And this will degrade your signal to noise, right? So you can actually the trick part here is to look at what matters, and this is signal to noise or carrier to noise ratio, and so it's not the raw power, because you can have a signal of high power but very poor signal to noise ratio. Okay. All right. So calculate the signal power at the output of the transponder. So see how this is going to be Cn plus the gain of the transponder, everything in dB. So this is minus 99.62 dB watt plus 110 dB, and this is
So GTX or GXP?
GXP. Let's just do the next. So this is 10.38 dB, which is 1091 watts. So that's how much the transponder is being. So these are kind of problems. You should always expect one problem like this. You know, it's an easy problem, but exercises basic calculations around the link budget. Okay, let me do another one.
Sir, what happens to the noise at the output of the transponder? It stays the same? So it's going to be multiplied by input.
The noise that is at the input of the transponder. Remember how we treat the transponder? We take the whole system and calculate the system noise temperature, which means you take all the noise out of the system and put it up front. So that's why that system temperature is 500 K and not 270. Out of that 500 K, 270 is because you're staring at the hot earth, which has a temperature of 270.
And
Right?
the other one is noise.
The other one is the noise temperature from internal components to the transponder. Transponder in this model is noise free, right? But all the noise is moved to the input. Now that is assuming that you are working within the dynamic range of the transponder. Because if you start overdriving transponder, then you get additional noise from nonlinearities, right?
So we didn't have any backup in this case.
Well, we are assuming, we are not dealing with that now. I'm going to introduce, if nothing is said, assume that you're in a linear region. But if you're doing problems, be cognizant of that thing. How do you understand that? I mean, you can go through the detailed analysis, but I know a lot of you are musicians, so you know that if you play any instrument, right, through the amplifier, if you play it at a low volumes, it comes out clean, right? But start cranking the volume. What happens, eventually you overdrive the amplifier. And what that does, the signal becomes noisy, right? And part of that noise is outside of the audio range, but part of that noise falls right in the range where your signal is, and your signal is distorted, right? In a lot of instruments, that's a desired effect, but here it's not, right? Here, it actually impinges upon your ability to determine what was the signal that has been sent. Right? Raises the noise floor. Right? We call that overdrive, right? In music. All right. So number 2. So satellite in problem 1 serves CONUS. CONUS is continental US. Essentially these 48 states that are connected to one another. The antenna, so now we're looking at the down. The antenna of the satellite transmits at a frequency 3.875 gigahertz. So that's a downlink from the satellite. And the Earth station is at the distance to the Earth station is 39,000 kilometers. So the antenna has an east-west beam width of, so theta east-west is 6 degrees, and theta north-south is 3 degrees, right? If you look at US, it's wider than tall, right? So there's more degrees this way than this way. The receiving Earth station, so receive at the Earth station has a 53 dB of a gain, and system temperature of 100 K. The has a okay, and is at what is it? Delta L is minus 3 dB. So we are on a minus 3 dB contour relative to the main beam of the antenna. Assume that the transponder power is 10 watts. So PT, as we calculated, is 10 watts. Remember, in the previous problem we calculated it's 10 watts. And assume efficiency, antenna efficiency of 0.6. Calculate the gain of the satellite antenna towards the Earth station. How would I calculate that? Oh, because from this data. Okay, right. Sorry. Calculate the gain of satellite antenna. Okay. So we have that equation theta 3 dB was equal to 75 lambda over the dimension in a given direction, right? So from this is the antenna that has unequal theta 3 dB. So you can assume that this is a horn antenna. Now, if you want to have a tighter beam width, smaller beam width, the dimension in that direction needs to be longer, right? So if our pattern looks like this, then our antenna needs to look opposite of the pattern. So here's what I'm trying to say is there's 3 degrees this way, and there's 6 degrees this way. So our horn antenna needs to be longer. This needs to be like this, right? Okay, to focus more energy this way than relative to this way. So first thing first, let's calculate lambda. Lambda is C over F. In our case, this becomes 3 times 10 to the 8 meters per second divided by frequency 3.875 gigahertz. Okay, or we put it times 10 to the 9 hertz, and this gives you a lambda of 0.0774 meters. So the dimension east-west is going to be 75 lambda divided by theta 3 dB east-west. In our case, this becomes 75 times 0.0774 meters divided by, this is 6. So this is 0.9677 meters. And the dimension north-south is 75 lambda divided by theta 3 dB north-south, which becomes 75 times 0.0774 meters divided by 3 degrees this time. And this is 1.935 meters. So we are 1.935 meters this way and 0.9677 meters this way, right? To focus to give the coverage to the continental US. Now, gain on the axis. We have the formula that the gain is going to be equal to your efficiency times 4 pi over lambda squared times the physical area of the antenna. In our case, this becomes 0.6 times 4 pi divided by 0.0774 quantity squared and times the product of these two. So it's going to be 0.9677 times 1.935. When you calculate the gain here, this is 2,356.7, which is 33.72 dB. So that's the gain of the antenna on X. Part B. Calculate carrier power and the receiver of the Earth station. So part B, let me redraw my picture now. Now we have a different, here's our satellite that received the signal. Now it's rebroadcasting towards this Earth station here. And we have calculated that this gain is 3372 dB. We know that this gain is 53 dB. And we're wondering what is the signal received at this point in dB watt. So we need to obviously calculate again, EIRP, free space path loss, and then so I guess EIRP towards Earth station is going to be is 10 watts, which is 10 dB. Let me just do this. Write the actual symbol. So this is going to be T transmit from the satellite in dB watt plus the gain of the satellite antenna. Let me call this gain S. Indicate satellite antenna in dB, and plus this delta L that shows us, where we are relative to the main axis of the transmit antenna. We're off the main axis. We're 3 dB from the main band. So this becomes 10 watts, or rather 10 dB watt. Plus the gain of the satellite antenna, 3372, and minus 3 dB, and minus 3 dB for being off axis. So this is 4072 dB watt. That's the EIRP of the satellite towards the Earth station. Free space path loss in this case becomes 9244 plus 20 log of the frequency in gigahertz, 3.875, and then plus 20 log of the distance in kilometers. And when I calculated this, it ended up being 196 dB. You're expecting to see that because you're at a lower frequency than on the uplink. On the uplink, remember, we were 199 dB. Here we're relatively small. So now, power received at the Earth station becomes now EIRP minus free space path loss and plus the gain of the Earth station antenna. So this ends up being 4072 dB watt minus 196 dB, and the plus gain of the Earth station, which is 53 dB. When you calculate this, well, when I did it, I always have a disclaimer. You end up with minus 102.28 dB watt. And this is the same as C, right? Your carrier power of your signal. Part C is calculate the noise power at the earth station within the 36 megahertz of the noise band. So calculate noise power at the earth station the noise power at the earth station in dB watt is going to be 10 log of KT system at the earth station times the bandwidth of the noise. The earth station, this is 10 log, this is 1.38 times 10 to the minus 23 joules per Kelvin times, what was this, 100 or 150? What, I remember. 100, right? 100, and then times 36 times 10 to the 6 hertz. And this ends up being minus 134.04 dB watt. Now, what is the C to N in this case? C to N on a down is equal to what? Is equal to C in dB watt minus N in dB watt, which in this case ends up being minus 102.28 dB watt minus 134.04 dB watt. And this gives you C to N on the downlink of 30.78 dB. Now, if we concatenate this with the first problem, this is the end of the problem, right? But let me ask you this: when we did this uplink calculations, right? We determined that C to N on the uplink was 26.4 dB, and then C to N on the downlink, C to N on the downlink was 30.78 dB. What is the overall C to N? One over, but what is the result?
Close to 30.
Close to 30 or close to 26?
30 to 26.
Close to 26. Remember, the C to N acts like a parallel resistance, right? The resistance is predominantly determined by the smaller one, right? It was already 26 dB here. And all we have are the gains and losses. Gains and losses cannot change your C to N, right? Your transponder amplifier amplifies both signal and noise, but C to N stays the same. Your free space path loss attenuated both your signal and your noise by the same amount, so C to N didn't change. The C to N has to degrade because there is some additional noise at this point. But C to N that comes, the signal plus noise that comes from the transponder, by the time it reaches its earth station, is more than 30 dBs above the locally generated noise, more than 1,000 times strong. So you have an elephant and a mouse, and combine the two is just an elephant still, right? So the noise that comes from the noise figure of the LNA at the earth station and from the radiation from the outer space is 1,000 of the signal and noise combined that comes from the satellite. So its contribution is negligible. So really what happens here is this 26 is predominantly what determines the overall noise of the signal to noise ratio. All right, let me do the next one.
Excuse me, where did you get the 26?
Where did I get, which one?
26
Maybe it's talking about-
Oh, from the problem number 1.
Oh.
Remember, this is the continuation. We split the problem into 2. So in problem number 1, we dealt with this side, or problem number 2, we dealt with this side. And I kind of asked you to combine the two.
So we always expect that C to N at the downlink is greater than the uplink, right?
No. As a matter of fact, it's quite the opposite, right? This link here is a weak one. All right. So usually this is the one that in this problem it ends up being the other way around. But in most cases, this is where the power is limited. So this is the one that is stretched. Theoretically and practically, right? You can actually say, oh, okay, this is 26. Let me increase the power here. And you just get a more powerful antenna or more bigger antenna or more powerful amplifier. And you bring this C to N to whatever it needs to be. Here, it is much more cost prohibitive to do that, right? So really, most of the time, this link is limited. But in general case, you know, we, as you all kind of remember this formula, C to N uplink -1 plus C to N down -1, right? So the larger the C to N is relative to the other one, then it matters less. Let's say if this one was, you know, all of these are linear, right? So if this is, let's say, 20 dBs larger, 100 times, then you have something plus something that's 100 times smaller. So it's really just the one that is smaller that determines the overall. And if you have that they're equal, then the overall is 3 dB lower. If one 10 dB larger than the other, then it's 0.4 dB difference. And if it's 20 dBs, then really you just look at the small one. Here, all the quantities are in linear. The C to N's are in linear. Okay, this is problem number 3. It says a 1411 gigahertz, so we have 1411 gigahertz operation. What band are we talking about here?
K.
KU band. Has a transponder with a bandwidth of 52 megahertz. Which is operated, so let me just read it. 1411 gigahertz satellite communication link has a transponder with a bandwidth of 52 megahertz, which is operated at the output power level of 20 watts. So this is from the satellite, we have 20 watts of the output power. And transmit antenna gain at 11 gigahertz at 30 dB. So gain satellite is 30 dB. This is on a downlink, so obviously it's at 11 gigahertz. Towards a particular earth station. Path loss to the station is 206 dB. So we're given as free space path loss is 206 dB. Including clear atmospheric losses. The transponder is used in FDMA mode to send 500 BPSK voice channels. So 500 BPSK voice channels. With a symbol rate, which is the same as a bit rate, 50 kilosymbols per second, and requires a receiver with a noise bandwidth of 50 kilohertz. So our noise is 50 kilohertz to receive the voice signal. The earth station used antenna gains. So the gain of the received earth station is 40 dB, 1 meter in diameter, and the receiver has the system noise temperature of 150 K in clear air. The IF bandwidth, so the noise bandwidth is 50 kilohertz. Okay, so let me kind of draw what this is all about first. You know, I always say, draw these pictures. I mean, they're trivial, but they kind of help you understand what is going on. So you have a satellite, and then you have multiple here earth stations that are on the down. Now, this guy here assembles a signal that has, what did it say, 500 voice channels. So there are 500 voice channels. Each of them 50 kilohertz wide. Now, if you take 500 times 50, what does it give you? 25 megahertz, right? So that means that there are substantial guard bands in between these FDMA channels, right? You have a few kilohertz, so 25 kilohertz on each side, or even something comparable to that. Now, you assemble this, you send this aggregate link, the satellite receives it, and then broadcasts it down, right? And all of these earth stations would receive it. They would decode all of them, but channel by channel, and then depending on where the signal is going, even though I may decode the channel 5, I discard it because it was really meant to this particular earth station, and there's a telephone line here that receives that channel. Right? So you would have switching that goes up. This is the rotary phone, right? That kind of goes with these kind of systems. That's when this is how it used to work. But what I'm kind of trying to pinpoint out here is this FDMA concept. You have frequency division multiplexing here, then you send this, and all of the satellites would receive the same signal, but they would pick the proper portions of the signal that is directed to them, and then discard the rest of it. Now, what are the questions in this problem? It says, calculate power transmitted in a single voice channel from the satellite. So calculate power transmitted in a single voice channel. Now, to the or from the satellite? From the satellite. So power per channel is going to be your total transmit power from the satellite divided by 500, because you have 500 channels. So this gives you 20 watts divided by 500, which is 0.04 watts per channel, which is minus 14 dB watt. Now that's a small power. But what is also small relative to all the other examples that we did? The bandwidth, right? So really what matters is not so much the power, but the power spectral density, right? And what else tells us that that's only thing that matters. Shannon's incapacity formula. The ratio there underneath the log is really 1 plus power spectral density, power divided by the bandwidth of the signal. So that's the power transmitted from per channel. B, calculate C to N in clear air for an earth station receiving the signal. So calculate C to N in clear air. Well, C to N in dB is going to be C in dB watt minus N in dB watt. What is C? C in dB watt becomes your power transmitted, so it's going to be minus 14 dB watt minus the free space path loss, which is 206 dB, and plus 40 dB of the antenna gain. Right? So, oh, what did I forget? See, I should always see whenever I deviate from my algorithm, I start making mistakes. So this is the power, right? But what is it that I want to have? I want to have ERP.
Yes.
And then plus 30 dB. So this is the EIRP in dB watt minus free space path loss of 206 dB and then plus 40 dB of the earth station antenna. So when you calculate this, this gives you minus 150 dB watt. Now the power of the noise in dB watt is going to be your 10 log of your K times Ts times the bandwidth of the noise. And in this case, this becomes 10 log 1.38 times 10 to the minus 23 joule per Kelvin times the temperature of the system is 150 K. And the noise is 550 times 10 to the 3 hertz. And when you calculate this guy, this is minus 159.9 dB watt. So your C to N in dB is going to be minus 150 dB watt minus 159.9 dB watt, which is 9.9 dB. And then the last question says, well, what is the margin if I know that BPSK requires C to N of 6 dB? So this is part B. What is the margin? Over, I guess, required 6 dB. Right? Well, the margin, by the way, delta C2N is going to be this 9.9 dB minus 6.9 dB, or 6.4 is 3.9 dB. So you have 3.9 dB of margin that for additional losses, and you're still going to maintain the channel up. I'm going to skip the next problem, it's trivial. Let me just work on the problem number 6. Yeah, squeezing it here. Okay. So, problem number 6. It says a geostationary satellite carries the transponder with a 20 watt transmitter at 4 gigahertz. So the satellite is 20 watt and the operating frequency is 4 gigahertz. The transponder is operating with a 3 dB backhaul. So 3 dB backhaul is 3 dB. And drives an antenna of 30 dB. So the satellite antenna is 30 dB. And earth station at the center of the satellite coverage area is at a distance 38,500 kilometers. And then it says calculate. Flux density of the at the earth station in dB watt per meter squared. All right, so flux density at the earth station in dB watt per meter squared. Now, here's the one of those inconsistencies, right? So let's first remember what the flux is. Flux
D or D?
hmm?
D cross H.
Say it.
Oh, H or D?
D cross H.
Yeah, that's but the way how we calculate this is transmit power divided by kind of the gain of the transmit antenna divided by 4 pi r or 4 pi b squared. Right? We're looking at the total power, right? What you're referring to is Poynting's vector, and Poynting's vector has a dimension of the flux, and if you're so Poynting vector cross dotted with the vector of the surface gives you the flux to that surface. But in this case, it's much more simple. We are assuming that you're radiating from this point, and we're looking at the sphere, and then essentially flux tells you, how is the energy distributed across the sphere. And then really what this tells us also, how does the antenna do its magic, and it's actually just shapes which way the power goes, right? So that's this. This would have been isotropic antenna, and then GT is there to tell you how much better this particular antenna is than isotropic antenna. Now, this can be also written as EIRP in linear divided by 4 pi r squared. So if I take the 10 log of both sides of this equation, then you get 10 log of your flux is equal EIRP or EIRP in dB watt minus 10 log of 4 pi r squared. Now, the question, it always comes back to, well, this is in certain units. You cannot really take the log of something that's not pure number, but we do it anyway in satellite communication. So the way how we go around it, we assume that there is a unit dividing this one here. So the way how we say your flux in dB watt per meter squared, which really means 10 log of your flux divided by 1 watt per meter squared unit, reference unit, so that you get the pure number here, is going to be your EIRP in dB, and then this quantity is in meter squared, right? So I can say minus 10 log of 4 pi, and then minus 10 log of r squared divided by meter squared. Now, when you do this kind of things, right, it's very easy to make mistake. Like, for example, here, if you were to use this equation and forget that r is given in kilometers, you're going to get mistake right away. So you have to translate this r into meters before you use this one. But let's just complete this problem here. So what is your EIRP? Your EIRP is going to be 20 watts, which is, I don't know, why do I have 40 dB watt? could I make a mistake here? Oh, no. Okay, so, see, EIRP in our case is gonna be transmit power in dB watt plus the gain of the satellite antenna in dB minus your backoff in dB, but you're not really transmitting at the full power. So this is 20 watts, that's 43, no, it's 13. 13 dB watt, 43 dBm, right? Plus gain of the satellite antenna is 30. And then minus 3 dB of the backoff, which gives you 40 dB watt, even as your EIRP. And the rest of it you just substitute. So you get W in dB watt per meter squared is going to be equal to 40 dB watt minus 10 log of 4 pi, that's 11, right? Yeah, 11 minus 20 log of the distance. So the distance is 38, 500 times 10 to the 3 to get it in meters. And when this is calculated, you end up minus 122.7 dB watt per meter squared. Now just as a point of control, when you do everything in logarithmic units, the values that you get for flux in dB watt per meter squared is going to be on the order of the typical powers that you get. Be cognizant, right? Because remember, this is per meter squared. If you were to get the power, you would take 10 log of the size of your antenna and add to this. Well, antennas are about meter squared, right? Smaller or a little bit bigger, but that's the order of magnitude. So this is, if this was into the antenna with the effective aperture of 1 meter squared, this would have been the power, exactly. So why am I telling you this? Because if you mess up the units, chances are you're going to get here something next 160 or make 35 or something that is unrealistic for the power. So, and that therefore it's unrealistic for your power flux as well. Part B. Part B says the power received by the antenna with a gain of 39 dB. So now I have this flux coming into the antenna that has a gain of 39 dB. So gain of the receive antenna at earth station is 39 dB. So the power received at your station is going to be your EIRP in dB watt minus the free space path loss in dB and plus the gain of the received antenna in dB. I already calculated EIRP was 40 dB watt minus free space path loss. I guess I need to calculate that one first. So free space path loss in this case is 92.44 plus 20 log of the frequency 4 gigahertz and plus 20 log 38.5 kilometers. So this ends up being 196, yeah, 196.19 dB. So 196.19 dB, and then plus 39 dB, which gives me the the receive power is -117.19. All right, and you can see that this compares to this, right? It's within a few dBs of one another. And that's essentially the size of the antenna. And you see what's left here. Okay, so let me start. I'm going to skip a few problems here and go through this problem 12. It's a little bit longer one, but it combines both links, so let me see if I can pull it off before the end of the class. So, are you ready? Can I start from here? So this is problem 12. It says design a communications link through a geostationary satellite to meet C2N margin specification. Path to satellite, so distance is 38,500 kilometers. And then there's a lot of data here, so let me just put it on the board. So for satellite, we have that this is a geo satellite at 73 degrees west. It has 24 C-band transponders. And then it has 24 KU band transponders. It has 3.2 kilowatts of RF power available. Antenna gains, TX and RX, so C-band, so for both bands, antenna gains, GTX equal to GRX equal to 31 dB. RX has a system noise temperature of 500 K. Transponder saturated output power is the saturated is 40 watts for C-band, and here the noise bandwidth is 36 megahertz, and then saturated power is 80 watts for KU, and the noise bandwidth here is 54 megahertz. So this is all satellite data. And then for signals, or sometimes referred to as waveforms, I have here FM TV analog signals with bandwidth of 27 megahertz and multiplexed digital TV signals, digital TV signals with QPSK. All right, well, all of that, there's a lot of data, but really what we care about is C2N needs to be 9.5 dB. And so Okay, so these are all input data, and we're going to go back to them as needed. So now design. So this is 12.1 section of the problem. It says design a transmitting earth station to provide clear air C to N. So C to N on the uplink needs to be 26 dB through a C-band transponder at a frequency equal to 6.285 gigahertz. Use the uplink antenna with diameter of 9 meters. Wow. So diameter here is 9 meters. And aperture efficiency is 68%. And find the uplink transmitter power to achieve the required C to N. The uplink station is located at, so delta L is going to be minus 2 dB. Allow the clear air loss is 0.5 dB. Okay. So again, it's always useful to draw what is it that we are required to do here. Here's your humongous Earth station antenna talking to this satellite here. This is the link that we're designing. Now, this antenna here has a diameter of 9 meters and is 0.68 is the efficiency. This antenna here has a gain of 31 dB, but we are at delta L of minus 2 dB, so we are not in the main beam of this antenna here. And what we need to determine is, we need to determine what is the required power on the what is the required power from this Earth station. So first let us calculate the gain of this Earth station here. Gain transmitted at the Earth station is equal to the aperture efficiency d over 2, which is r squared times pi, which is the physical area of this particular antenna. So and then that times 4 pi over lambda squared. So in our case, this becomes 0.68 times 9 meters squared over 4 times pi times 4 times pi divided by lambda squared. Lambda squared, I'm just going to write this as 3 times 10 to the 8 meters per second divided by your frequency of operation 6.285 times 10 to the 9 hertz, and then squared. So that will give me the gain of the Earth antenna. Of course, this would be in linear, so when you calculate, this ends up being 238,595, which is 53.8 dB. So huge antenna, therefore huge gain that this guy has. So now, uplink link budget here. Okay. We're going to say first, let's calculate the noise. The noise is going to be 10 log of KT system times the noise bandwidth. It's going to be 10 log 1.38 times 10 to the minus 23 joule per Kelvin times 500 Kelvin. That's the system noise temperature of the satellite receiver. And then times the bandwidth, since we're working in a C-band, this is 36 megahertz. 36 times 10 to the 6 hertz. This gives us the noise power and the input of the transponder to be minus 127.3 dB watt. Okay, so C to N in dB is equal to 26 dB. Since I know N, I can determine that C in dB watt needs to be equal to N in dB watt plus C to N in dB, which is noise in dB watt is minus 127.3 dB watt plus 26 dB, and this gives you that the power of the signal from the earth station needs to be minus 101.3 dB watt. So that's the signal power that I need to provide at this point here. Well, that signal power is going to be whatever you deliver to the antenna in dB watt plus the gain of the earth antenna in dB minus delta L, or rather plus delta L because I had it in negative over there because you're off the main beam of this antenna here. Then minus free space path loss, and then plus the gain of the receive antenna at the cell. Right? So the only thing that I don't know as of yet is what the free space path loss is, so that's easy to calculate. Free space path loss is going to be 92.44 plus 20 log of frequency in gigahertz, which in this case is 6.285, and then plus 20 log of 38500 kilometers. So this is 200.1 dB. So now substituting everything in there, the only thing that I don't know is PT. So PT in dB watt is going to be equal to C in dB watt minus the gain of the antenna in dB watt, dB, sorry, minus delta L in dB plus free space path loss in dB and minus the gain of the receive satellite antenna in dB. So this is equal to minus 101.3 dB watt minus 53.8 dB plus this gain of this correction for being off the axis plus 200.1 dB and minus gain of the receive antenna, which was 31 dB. And that calculating gives you the transmit power of 16.5 dB watt, which is 44.7 watts. So around the 50 watts of ERP will get you from the earth station to the satellite and give you proper seed plane.
Professor,
0.5.
you can only get minus 127.3 if you use 27 megahertz bandwidth for noise.
For this guy.
Yes, if you use that, you get minus 127.3.
Okay, so that's what I did, I guess. So 27. I guess the satellite C-band is used for the analog signal, and the noise bandwidth is 27. Just this whole satellite is 36.
So then what do we use that 36 megahertz for?
I guess whatever it said in the problem, I be careful. If I ask you to do that in a test, I will always say which one is the noise bandwidth. You use the noise bandwidth.
The signal.
So that's the one that is specified, and it's never the entire bandwidth of the transponder because you have to have the guard bands. All right, so let me stop here. I'll try to post the rest of it. You will find some more problems there.
What about considering the air loss, 0.5 dB?
0.5 dB, I might have forgot that as well. So this should be 0.5 dB bottom. So this there's a free space loss plus I need to add here plus
Minus.
plus the clear air
That's it.
loss. All right, so plus 0.5 dB, and then plus 0.5 dB here, so it's 17 dB. All right, 17 dB watt. How many watts?
50.
So 50 watts. Well, okay. That's it for today.